History of Mathematics, Lecture 15. And we've been studying the work of Isaac Newton. And what we did last Wednesday was Newton's binomial theorem, which I will review also. So let's just review. We have what is now called Pascal's triangle. So this is a triangular array of positive integers. And there's a simple rule to construct it. You start with the number 1. So in this row, there is one number. And in the second row, there are two numbers, 1 and 1. And 1 is 1 and 1 is 1. Now, the third row, or the next row, it's really, in our sense, the second row, but we'll have 3 numbers. At the ends, they're always 1s. And in the middle, each number is the sum of the 2 numbers in the preceding row directly above it. So 1 plus 1 is 2. In the next row, you put 1s at the ends, and inside 1 plus 2 is 3, and 2 plus 1 is 3. And the next row, there's a 1 at each end, and inside 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. And in the next row, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. And this is so much fun, I'll do another row. In the next row, 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6. And the way we enumerate these rows is this is row 0. This is row 1. This is row 2. This is row 3, and so forth. Right? So this is row 6. And if you look at the nth row, the nth row always has the following form. You have 1, n, other stuff, and it ends up n and 1. Right? So this is what the nth row looks like. And so if you think of, and this nth row has n plus 1 numbers in it. Like row 2 has 3 numbers. Row 3 has 4 numbers. Row n is n plus numbers, n plus 1 numbers. And the kth number in this row, so n plus 1 numbers, the enumerated k equals 0, 1, 2, 3, up to n. Right? So this is the 0th number, and this is the nth number. And the kth number is usually written n over k. It's not a fraction, just n over k with parentheses. This, I feel like it's like a 2-by-1 matrix, but just n over k. And this is red, and this number is called the kth binomial coefficient. And we can say exactly what this number is. What is the number that is the kth number in the nth row? It can be written as a fraction. The denominator is n factorial. I remind you that for any n, any positive integer n factorial is the product of all the numbers up to n for a positive integer n. 0 factorial is just defined to be 1. So for example, 5 factorial is 1 times 2 times 3 times 4 times 5, which if you multiply it out is 120. Right? And the kth binomial coefficient, the kth number in this row where k goes from 0 to n, is k factorial times n minus k factorial divided by n factorial. So for example, if we look at this row, this is row 4, and these numbers, there are 5 numbers as you go across. This is the 0, 1st, 2nd, 3rd, and 4th. So this number is entry 2 in row 4. So this number, for this number, we are in row 4, and the entry k is equal to 2. So 4, this is usually read n choose k. So the binomial coefficient for choose 2 is what? N is equal to 4, so we have a 4 factorial in the denominator. K is equal to 2, and n minus k is 4 minus 2. Right? Let's see, what is that? 2 factorial is 1 times 2. 4 minus 2 is 2. 2 factorial is 2. 4 factorial, 1 times 2 times, oh, sorry. What I just said is, I had this is backwards. The binomial coefficient is n factorial over k factorial n minus k factorial. That's what it is. So 4 choose 2 is 4 factorial over 2 factorial times 4 minus 2 factorial. 1 times 2 times 3 times 4 is 12. 2 factorial is 2 times 2. This is 12 over 4. This is 3. So why am I getting everything wrong here? Why am I getting everything wrong? 2 times 3, oh, it's 24. 4 factorial, 1 times 2 times 3 times 4 is 24. So this is 24 over 4, which is 6, which is what it's supposed to be. Glad I finally got it right. Let's do another one to see if I can do it correctly this time. Let's take this coefficient. So this is row 6, k equals 0, 1, 2. So if n is equal to 6 and k is equal to 2, 6 choose 2 is 6 factorial over 2 factorial times 6 minus 2 factorial. What is 6 factorial? 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. The product of the numbers from 1 through 5 is 120. This is 120 times 6. So this is 720. This numerator is 720. Over 2 factorial, which is 2. 6 minus 2 is 4. 4 factorial is 24. So 24 into 720 goes 30 times, and 2 into 30 goes 15 times. So we get 15. Right? That's what we get. Right? Any questions about this? So this is Pascal's triangle. It's a very beautiful array of numbers. Just to see if you can do the calculation, recall n choose k, this binomial coefficient, is n factorial over k factorial n minus k factorial. So compute 7 choose 3. And I will pause for a moment to give you a chance to do that calculation. So in this case, n is 7, k is 3, n minus k is 4. So if you do the calculation, this is going to be 7 factorial divided by 3 factorial times 4 factorial. See, what is that? Can someone give me the answer? We don't even have to multiply out these factorials. Let's see. 7 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 over 3 factorial times 4 factorial. So 1 times 2 times 3 times 4 in the denominator cancels out the 1 times 2 times 3 times 4 in the numerator. 2 times 3 is 6. So this 6 cancels this 6. And we're just left with 5 times 7. So the answer is 35. The answer is 35. And one reason why these numbers are called the binomial coefficients is because they come up when you expand the binomial 1 plus x to the power n. So for example, 1 plus x to the 0th power, anything to the 0th power is 1. 1 plus x to the first power is 1 plus x. 1 plus x squared is 1 plus 2x plus x squared. 1 plus x cubed is 1 plus 3x plus 3x squared plus x cubed. And if you look at the coefficients in these polynomials on the right-hand side, this is 1. This is 1 times x, 1, 1. This is 1, 2 times x, 1 times x squared. This is 1, 3, 3, 1 times x cubed, 1, 3, 3, 1. What you see over here is Pascal's triangle. And in general, if you take 1 plus x and raise it to the power n, you're going to get a polynomial of degree n. With some coefficients. And this is going to be 1 plus nx plus, this is going to be, well, in general, the coefficient of x to the k is going to be the kth binomial coefficient. This will be n choose 2, n choose 3. In general, when you take 1 plus x to the n and you expand it, you get a polynomial of degree n. And the coefficient, so for k going from 0 up to n, the coefficient of x to the k is the binomial coefficient n choose k. Right? So if you haven't seen this in calculus or pre-calculus or somewhere, now you see it, but no one should even, this is something you should know before you learn calculus, because this is really just a kind of higher level high school algebra.
I have a question.
Yes, sir. Go ahead.
Would it matter if it's a difference of squares? It's the same format.
What do you mean by a difference of squares?
Like it's if it was 1 minus x to the second.
Okay, so you have for any x, 1 plus x squared is 1 plus 2x plus x squared. That's a very good question. Right? I'm glad you asked that. Right. So this is 1 plus x squared. And you're asking about 1 minus x squared, for example. Is that right?
Yeah.
So you can think of 1 minus x as being 1 plus minus x squared. So this is still the form 1 plus something, but the something is minus x. So this would be 1 plus 2 times minus x plus minus x squared, which is 1 minus 2x plus x squared. Right? Do you see that?
Yeah.
Kind of clever. If you take 1 minus x cubed, that's like 1 plus minus x cubed. When you expand the cubic, you get 1 plus 3 times minus x plus 3 times minus x squared plus minus x cubed, which is 1 minus 3x plus 3x squared minus x cubed. All right. And in fact, you could also say if you have x plus y, any quantities, whatever they are, raised to the power n, this is going to be, see, what are the coefficients, the binomial coefficients? You're going to get x to the n plus n, x to the n minus 1, y. The kth term will be the binomial coefficient n choose k, x to the k, y to the n minus k, up to y to the n. Is when you expand this, it's like you're going across and you have monomials, which are x to the power, y to the power, and the sum of the powers is equal to n. You could actually get this from the same, you could write x plus y to the n is x times 1 plus y over x, all to the n. Because x times 1 plus y over x is x plus y to the n. I can factor out the x to the n, 1 plus y over x to the n. Like, for example, what is x plus y cubed? I could write this as x times 1 plus y over x cubed, which is x cubed times 1 plus y over x cubed. And then I can apply the binomial theorem for 1 plus something cubed. This will be x cubed, and I expand this. I get 1 plus 3 times y over x plus 3 times y over x squared plus y over x cubed. And when I multiply across, I get x cubed plus 3x squared y plus 3xy squared plus y cubed. All right, so from that, so knowing 1 plus x to the n gives many other results. Plus, you can put many things into this form. Now, this was known before Newton. So what was Newton's binomial theorem? It wasn't just repeating what had been known to, I'm not sure, Hugh, certainly in India and China, this was known. So Newton considered things like square root of 1 plus x. And he thought of this as 1 plus x to the power 1/2. So this is also a binomial, but the exponent is not a positive integer, it's a fraction. Or let's see, let me just pick another example that's maybe in the text. 1 over 1 plus x cubed. You can expand 1 plus x cubed, you get 1 over that, but an expansion of 1 over 1 plus x cubed, you can write this as 1 plus x to the exponent -3. So in both of these cases, this is really of the same form, 1 plus x to the n, but now here n was always a positive integer. Here it could be a fraction or a negative number. And let me explain how Newton's binomial theorem extends at least in retrospect, almost an obvious way, the classical binomial theorem. So Newton's binomial theorem the way it's written is you have to sort of redo it in more modern terms, but he wrote something in form P plus PQ to the m over n. And he wants an expansion of this somehow. So the first term is P to the m over n. See, in this case, for example, it's like P is equal to 1, Q is equal to x, because then this is 1 plus 1 times x, 1 plus x, and n is replaced by the fraction m over n. So the first thing he gets is P to the m over n. Right? P is 1. So 1 to any power is 1. You would get 1. The next term is m over n, the exponent, aq, and a is the previous term, p to the m over n. The next term is m minus n over 2n times bq, where b is the previous term. The next term is m minus 2n over 3n cq, where c is the previous term. The next term is m minus 3n over 4n dq, where d is the previous term. And so on. Now, you can see one kind of pattern here because you have these numbers m minus n over 2n, m minus 2n over 3n, m minus 3n over 4n. Those numbers look like let's see. What do they look like? If you have m minus n over 2n. That's a half m minus n over n. That's 1/2 m over n minus 1. If you have m minus 2n over 3n, take out the 3, m minus 2n over n, that's a third m over n minus 2. If you look at the third term, m minus 3n over 4n, that's, take out the 4, 1/4, m minus 3n over n, that's a fourth m over n minus 3. And in general, if you had the term m minus k minus 1n over kn, that would be 1 over k, factor out that k from the denominator, m over n minus k minus 1. So we get expressions that look like this. Now, let's work out what these things are. So we have m over n aq, and a is p to the m over n. So this is m over n, p to the m over n, q. What is the next term? M minus n over 2n bq. M minus n over 2n is a half m over n minus 1 times b. This is b, right? M over n, p to the m over n, q times q makes that q squared. So this is m over n minus 1 over 2 p to the m over n q squared. Let me calculate one more term. So the next term is m minus 2n over 3n cq. M minus 2n over 3n is 1 over 3 m over n minus 2. C, this is the term C. This is m over n minus 1, m over n over 2, p to the m over n, q squared times q is q cubed. Let me rewrite this. This is 1 over 3 times 2. That's 3 factorial in the denominator. 1 times 2 times 3. And in the numerator, I have m over n minus 1, m over n minus 2, q cubed, p to the m over n. So this is what we get when we're expanding p plus pq to the m over n. to make things a little bit simpler, suppose I let p equal 1. So then this would be 1 plus q to the m over n. And what we got was the first term was p to the m over n. That's 1. The second term was m over n q. The third term was 1/2 m over n minus 1 q squared. The third term, that's what I just calculated here, when p is 1, is 1 over 3 factorial m over n minus 1, m over n minus 2 q cubed. Hmm. So I just want to recall the binomial coefficient. I want to write it down in an alternative way. N choose k. This is n factorial over k factorial n minus k factorial. What is n factorial? It's the product of all the positive integers from 1 up to n. K factorial is the product of the integers up to k. N minus k factorial is the product of the integers up to n minus k. And I can see that there's some cancellation if I want to take advantage of it. Here I have the integers from 1 to n minus k. Here I have the integers from 1 to n minus k. And you can cancel them. So what we're left is a somewhat simpler fraction. The denominator is k factorial, and the numerator is the product of the k positive integers starting from n and going backwards. This is n minus 1, n minus 2, down to n minus k minus 1. So for example, if n is 6 and k is 2, 6 choose 2, that binomial coefficient is 2 factorial over 6 minus 6 times 6 minus 1, or 5. So we get 15 right away. So this is an alternative formula for the binomial coefficient. And if you think of n as a variable, let's say n is t, just to not use a letter we've used before. So for any positive integer t, t choose k is t minus 1, t minus k minus 1 over k factorial. And that's exactly the expressions we have here where t is m over n. So if you assume, if you want to define this as a function of t, if t is m over n choose k is 1 over k factorial, m over n minus 1, m over n minus 2, down to m over n minus k minus 1. That's exactly the coefficients we have from Newton. So one can see that Newton's binomial theorem is just a miraculous sort of generalization of the classical binomial theorem. In the classical binomial theorem, you have 1 plus x to the n is 1 plus nx plus, in general, you have x to the k, and the coefficient of x to the k is the binomial coefficient n choose k, up to x to the n. And Newton's, so this is classical, where n is a positive integer. And Newton says the following, and you might say, well, in this series, why doesn't it go on forever? So in this series, in the classical series, the coefficient of x to the k, where k is any positive integer, is the binomial coefficient n choose k that has a denominator of k factorial, and in the numerator you have n minus 1, n minus 2, down to n minus k minus 1. So for example, what would the binomial coefficient 5 choose 3 be? Right? Right? K is 3, 1 over 3 factorial. N is 5. So you would get 5, and you would get 3 terms. Let's see, 5. Wait, something's not wrong. Oh, sorry. I don't mean 3. That's perfectly okay. Suppose we have 3 choose 5. So n is 3, and k is equal to 5. So this will involve 5 terms. We'll have 1 over 5 factorial. So this will be n minus 1, n minus 2, n minus 3. 1, 2, 3, n minus 4. 5 terms. And when you plug in n equal 3, you get 1 over 5 factorial, 3, 3 minus 1, 3 minus 2, 3 minus 3, 3 minus 4. This term is 0. So this binomial coefficient n choose k, when k is bigger than n, becomes 0. So if you have 1 plus x to the n, and n is a positive integer, you could write this, if you like, as an infinite series. Right? N choose k, x to the k, but when k is bigger than n, these coefficients become 0, and this series stops after a finite number of terms. But if n is not a positive integer, you never get this cancellation, and the series goes on forever. So let's look at square root of 1 plus x. That's equal to 1 plus x to the 1/2. This is going to be 1 plus 1/2 choose 1x plus 1/2 choose 2x squared plus a half choose 3x cubed, plus a half choose 4x to the fourth, and so on. What are these coefficients? Remember, the formula is t choose k, or n choose k, is n minus 1. You have k terms in the numerator, starting with n and going down by 1, n minus k minus 1 over k factorial. So this is 1 plus 1 over 1. What is this term? I have a half minus 1 over 2 factorial x squared. A half choose 3, that's 1 over 3 factorial. A half minus 1, a half minus 2 times x cubed. Plus 1 over 4 factorial, a half minus 1, a half minus 2, a half minus 3, x to the fourth, and so forth. What are these numbers that we get? 1 plus x. A half times a half minus 1 is minus a fourth over 2 minus an eighth x squared. Plus this is 1/6 times a half minus 1, that's a half times minus a half, times minus 3 halves. A half minus 1 is minus, this is minus a fourth minus 3 halves. That's 3 over 8 x cubed. 3, this is really the same as 3 over 6, 1 over 16. What's this term? I have 1 over 4 factorial. 2 times 3 times 4 is 24, times a half minus a half minus 3 halves minus 5 halves x to the fourth. This is minus minus minus, makes this minus 15 over 2 times 2 times 2, 8 times 24, right? Whatever that turns out to be. Let's see. 3 into 15 is 5, and 3 into 24 is 8. Right? Oh, 2, 2, 2, this is 16. So this is really minus 5 over 128 x to the fourth. And if you were interested in how do you expand square root of 1 minus x, that's 1 minus x to the half, which is 1 plus minus x to the half. So it's the same series with x replaced by minus x. It would start off as 1 minus x minus an eighth x squared minus a 16th x cubed minus 5 over 128 x to the fourth, and so forth. So that's Newton's binomial theorem. So in getting to the great theorem, input 1 is Newton's binomial theorem for the square root of 1 minus x. Input 2 is quadrature. Remember, what is quadrature? For the Greeks, quadrature meant writing the area of some geometrical figure as the area of a square of the same size. Newton moved well beyond that, and he worked out a rule for finding, if you have the function y equal ax to the m over n, if you graph that, and when x is 0, y is 0, and when you get to some point b, this is the graph. Let's call this a, this b, and this point d. And what is the area under the curve? A equals xm to the m over n, from a equals 0 to b. The area, by the way, what would we do? The area would be the integral from here to here. Let's do it in our notation. In our notation, 0 x, and this is y equals ax to the m over n. This will be the integral from 0 to x of the function a, let's say t, to the m over n dt, right? That's the area under the curve. What is that? That's a. Integrating t to the m over n is 1 over m over n plus 1, t to the m over n plus 1, evaluated from 0 to x. Let's see, this is n over m plus n times a, x to the n plus n over n. So Newton discovered this. Newton discovered integration and this. So this is the second input into what is the grade theorem in this chapter. And the grade theorem, again, we're spoiled because we have calculators and computers. If you want to know what is the square root of 7 to 20 decimal digits, your calculator will give it to you. If you want to know pi to 1,000 decimal digits, your computer will give it to you. So, but this was a hard problem for hundreds or thousands of years. So Newton's approximation to the number pi. Right? So in this, we use the binomial theorem and we use this integration. Right? So this is the great theorem in this chapter. And as you recall, as you know, what you must know, this is the minimum, is how to prove the great theorems in all the chapters. So the great theorem in the chapter on Newton is his approximation to pi. And so let's see what he does. So draw a semicircle in the first quadrant whose diameter is 1. So the center is right here at a half comma 0. This is 1 comma 0. This is 0, 0. So this is a circle in the first quadrant, center at a half comma 0, with radius a half. So for example, this point would be a half comma a half. And if we go halfway from 0, 0 to a half 0, that's the point 1/4 0. And we draw the vertical line at this point. And I want to know, what are the coordinates of this point? So following the notation in the book, this is, let's say, point A, point B, point C, point D, point E. And I draw this radius. So this is a right triangle. This side is a half. Sorry, this side is a quarter. This is the radius of a circle. It's a half. So this side of this right triangle is half the radius, half the hypotenuse. That means this angle is pi over 6, or 30 degrees. If you have a right triangle where one side is half the hypotenuse, the acute angle is pi over 6, which means this angle is pi over 3, because these have to add up to pi over 2. So this is pi over 3. Right? Are there any questions about this? This is really the crux. This is one of Newton's beautiful ideas here. He wants to figure out, he wants to compute pi, and he's going to associate pi with a certain area, and he's going to compute that area in two different ways. What is the area that Newton is going to compute? He wants to compute the area which is bounded below by this line, above by this line, and on the top by this arc of the circle. Right? So the problem is to compute the area of the region ABD. And we're going to compute this in two ways. So if this is pi over 3, the area of the sector of the circle, ABD, sorry, ACD, this sector is what? It's 1/3. So this pi over 3 is a third of this angle. It's 1/3 the area of the semicircle. We have the semicircle, and if this is pi over 3, the area of this sector, ACD, is a third the area of the semicircle. What's the area of a semicircle? It's half the area of the circle of radius a fourth. Pi, sorry, of radius a half. The circle with radius a half, r is a half, pi r squared is pi times a half squared, and you take half of that. So this is pi over 8 times 3. This is pi over 24. So the area of this sector of the circle is pi over 24. The area of this right triangle, BCD, well, the area of a triangle is a half the base times the height, is 1/2 the base, which is a fourth, times the height. What is the height? The height is you have a 30, 60, 90 right triangle, or a right triangle with angles pi over 6 and pi over 3. This side is half of the hypotenuse, and this side is √3 over 2 times the hypotenuse, right? So if you have a triangle if this is a and this is 2a, this is root 3a. So when a is equal to a fourth, this is a half, and this is root 3 over 4. That's the height, root 3 over 4. So you get root 3 over 2 times 4 times 4, which is 32. So the area of this sector of the circle is pi over 24. The area of the triangle is root 3 over 32. So method 1, the area of the green region ABD is equal to the area of the sector minus the area of the triangle, root 3 over 32. That's that area. Area of the green area. But what about method? Well, that's another way to compute this. Method 2. Well, again, you have to know little pre-calculus. If you have the circle whose center is at a fourth and whose radius is a fourth, whose center is at a half and whose radius is a half, the equation of the circle is x minus a half squared plus y squared equals the radius squared. You have to know the formula for a circle with radius at a point and with center at a given point and a fixed radius. Let's expand this. This is, so for the semicircle, the equation of the semicircle is x minus a half squared plus y minus 0 squared, because the center is at a half 0, equals the radius squared. If you expand this, you get x squared minus x plus a fourth plus y squared equals a fourth. So y squared is equal to x minus x squared. So y is the square root of x minus x squared, or the square root of x times 1 minus x, or the square root of x times the square root of 1 minus x. Okay. So all of this is worked out in the same detail in the text. It's all there, and you should be looking at the text, of course. So let me just draw this picture again. 0, a fourth, a half. This is the semicircle. The equation of the semicircle is y equals square root of x, square root of 1 minus x. Yeah. And I'm interested in this green area. So this is x to the 1/2, 1 minus x to the 1/2. But a few minutes ago, I expanded 1 minus x to the 1/2 by Newton's binomial theorem. This is what I got. One minus x minus 1/8 x squared minus 1/16 x cubed minus 5 over 128 x to the fourth, and so forth. This is from Newton's binomial theorem. So this curve that describes the semicircle is y equals, let me just expand this, I get x to the 1/2, x to the 1/2 times x is x to the 3/2. This times this is minus 1/16 x to the 7/2 minus 5 over 128 x to the 9/2, and it keeps going. So the area under the curve, this is the green area, y equals square root of x, square root of 1 minus x. When you integrate this term by term, you get, remember, x to the m over n, when you integrate it, is 1 over m over n plus 1, x to the m over n plus 1, or n over m plus n, x to the m plus n over n. So you get, when x is 1/2, if you add 1, you get 3/2. So you get 2/3 x to the 3/2. When you add 1 to 3/2, you get 5/2 minus, oops. It should have been a 1/2 here. I don't know why I forgot that. Minus 1/2, 5/2 x to the 5/2, minus 1 over 16. 7/2 plus 1 is 2/9. So 2/9 x to the 9/2 minus 5 over 128, 2 over 11 x to the 11 over 2, and so forth. So you get 2/3 x to the 3/2 minus, oops, that's just 2/5, minus 1/5 x to the 5/2 minus 1 over 8 times 9 is 72 x to the 9/2 minus 5 over 64 times 11 is 704 x to the 11/2, and so forth. If you take this curve and you integrate it from 0 to x, this is what you get. And when x is equal to 1/4, you get the green area. What we're interested in is approximately, let's just look at these first 4 terms, 2/3, 1/4 to the 3/2 minus 1/5, 1/4 to the 5/2 minus 1 over 72, 1/4 to the 9/2 minus 5 over 7/4, 1/4 to the 11/2. We get this number. And 4 is 2 squared. So this is 2/3, 1/2 cubed. minus 1/5, 1/2 to the 5th, minus 1/72, 1/2 to the 9th, minus 5/74, 1/2 to the 11th. There are no more square roots in this. This is just fractions, right? So you can calculate this out. And we've calculated the green area in a second way. What did we get the first time? Yeah. When I calculated this the first time, I got pi over 24 minus root 3 over 22. So pi over 24 minus root 3 over 32 equals this. And this is an equation you can solve for pi. And when you do the calculation, you get pi is 3.14159. This is an approximation, but it's accurate to 7 decimal digits. That's the whole point of this. So let me review what I just did, because this is the great theorem that we want to try to understand. So in this chapter, the great theorem is Newton's approximation to pi. And he does it in two ways. First, you take the circle, the semicircle, with center at a half zero, and radius a half. So this is the 0.14, this is the 0.1/2. And he's going to find two ways to compute this green area. So the green area, on the one hand, is equal to the area of the sector of the circle ABCD minus the area of the triangle BCD. The area of the sector of the circle, this angle is pi over 3. So that's a third of the area of the semicircle, which is a half. So it's 1/3 of the area of the semicircle, which is a half the area of a circle, of radius a half. So 1/2 pi 1/2 squared. And the area of this triangle this point is a fourth root 3 over 4. This is a half. This is a fourth. So that's a half, the base times the height. So this is 2 times 4. This is pi over 24 minus root 3 over 32. But on the other hand, the equation of the circle with center a half, comma 0, and radius a half is this. X squared minus x plus a fourth plus y squared equals a fourth. The 1/4 cancel, you get x squared minus x plus y equals 0. Or y equals x, y squared is x minus x squared. So y is the square root of x minus x squared, which is the square root of x times the square root of 1 minus x. And we expand this by Newton's binomial theorem and integrate. That's what we do. So I encourage you strongly, strongly, strongly to study the text, to understand the proof, and if you have questions, again, ask me at the start on Wednesday. I always start by asking for questions, and or come to one of our Zoom sessions. The next one I think is tomorrow at 7 in the evening.
You don't have one today?
If you want one today at 7, I can set it up. Just send me an email and let me know.
Okay.
Right. But I can add one at 7 if, but I won't remember unless you send me an email. And if you do, then I'll announce it to everyone. But yes, I can do 7 tonight if you want. Okay. So we're moving along. We got out of the era of the Greeks. We got out of the 17th century Italy, and we're getting into the 18th century, where there's a huge explosion in our knowledge of mathematics. And from Newton, and then on Wednesday, we start the chapter 8, which is on Euler, spelled E-U-L-E-R, a great Swiss mathematician. Any questions before we stop for the morning? If not, enjoy the day and see you on Wednesday. Bye all.